Welcome to my channel. In today's video, we are going to look at a truly hard dynamic programming problem. This is burst balloons. Burst balloons doesn't get as much recognition as other DP problems like coin change, house robber, jump game. This one somehow gets glossed over even though it's a fantastic and a pretty hard DP problem. You are given n balloons indexed from 0 to n-1. Each balloon is painted with a number on it represented by an array nums. You are asked to burst all the balloons. If you burst the ith balloon, you will get nums I-1 times nums I plus 1 coins. If I-1 or I plus 1 goes out of bounds of the array, then treat it as if there is a balloon with a 1 painted on it. Return the maximum coins you can collect by bursting the balloons wisely. Shoutouts to Leetcode for including this problem in his interview prep. This is something everyone should struggle through at the first attempt. It took me a couple of days for me to even get a working solution, and it wasn't even optimal. Let's jump into the brute force sort of way of doing this. We're going to be looking at example 1 here. As the problem suggested, we are going to add ones to our bounds here to avoid an out of bounds exception. And this is a trick that you're going to learn as you keep lead coding. You'll find that by modifying the input slightly, we can come up with more clear and concise solutions. In this example, I'm going to skip over index 1 and we're going to go and burst the balloon at index 2 for illustration purposes. You'll see that the max coins that we are generating in this first burst is going to be 15. And you'll notice that our input has reduced. We've now eliminated 1. We've taken the subarrays on either sides of 1 and we've joined them together to create a new problem. And in this problem, we are going to check to see if we can burst our first element here, which is going to take elements from either sides of the subarray. So that means 1 here comes from the green side of the subarray, and 5 comes from the pink side of the subarray. And we're going to use both of these values to calculate our new total max coins that we've generated. We can use brute force recursion here to see what yields us the maximum coins possibly generated. We are performing a permutation problem here. We're trying to find the correct order of permutations that would yield us the maximum number of coins, and that is going to take us O of n factorial time. This is going to work for smaller inputs, but for bigger inputs, this becomes a problem. Now, if you were able to come up with a solution in an interview by yourself, and if you can somehow code this really quickly to show me that it works for small solutions, I would actually pass you. We are in a competitive landscape now. Most of you are going to vie for the optimal solution. So let's take a look at how that looks. This is the main trick, you guys. Once you understand that you need to start last, everything becomes simple. Again, I don't know how you're going to come up with this solution if you have not seen it before. Is 1 at index 2 the correct last balloon to burst to get the total maximum number of coins within the range of 0 to 5? Is the question that we are asking at this point. So this yields us in one of two possibilities. The first one is no. If 1 at index 2 is not the last balloon that we need to pop to get the maximum coins, then it's simple. We simply pick a different balloon to burst last. And we'll talk about evaluating this pretty soon. But this is pretty simple. You pick a different balloon. But if 1 at index 2 is indeed the correct last balloon to pop to get the maximum coins, then there are some things that you need to consider. All the balloons up until this point have already been popped. Any balloon to the left of 1 does not care about the values of the balloons that have been popped to the right of 1. And likewise, any balloons that have been popped to the right of 1 does not care about any of the values of the balloons that have been popped to the left of 1. You have to really understand this. If 8 was being popped, if 8 at index 4 was being popped, then it only relies on its immediate left and right balloons. 5 at index 3 and 1 at index 5. But if 5 was already popped before 8, then 8 at index 4 will use 1 at index 2 as its leftmost value. So what I'm trying to say here is, this 1 at index 2, if it is the correct last balloon to pop, it sort of acts as a wall. We've essentially created two independent contiguous subarrays that don't really care for each other. And this is very different from what we saw in the permutation solution, where when we tried to pop a balloon, we would take elements from either sides of the subarray to calculate our cost. But by working backwards, we've established that we can create subproblems because we've made independent contiguous subarrays that can generate values that are not dependent on each other. What I'm claiming here is there's some value y that represents the maximum number of coins burstable between the ranges of 0 and 2. And there's some value z that represents the maximum number of coins burstable between indexes 2 and 5. So that means y plus bursting our last balloon at index 2 plus z would yield us the possible answer to this question. Now, if I were to rewrite this a little bit with code, this is what it's going to look like. Y can essentially be the result of a recursion that takes in the index ranges 0 and 2 in this case. And if you add that with bursting our last balloon at index 2, and if you add that with z, which can be essentially the result of a recursive function that takes 2 and 5 as its left and right indices, then we could potentially come to our answer. And if I were to extract these values out into variables, this is what it's going to look like. So we'll have some value left and some value right, and we're going to go through every index I between left and right to calculate the maximum value that we could generate in this range. And if I were to represent this in formula, this is what the formula is going to look like, and this is it. So we can represent this in a for loop, and inside this for loop we're going to go through the range left and right, and we're going to go through a recursion, and we're going to use it to calculate our max coin. So we're going to be in our first depth, so I'm not going to go into the recursion just yet. We're just going to go through, and we come to the end here. It so happens that for this particular example, 8 is indeed the last balloon that you have to pop. So if we go into this, notice that our range has decreased. So now it's from 0 to 4. And within this range, we are going to pick the last balloon that we need to pop. But in the overall problem, this becomes the penultimate balloon that we need to pop. And for this example, it happens to be 3. And now our range has further decreased from 1 to 4. And within here, we find that 5 is the balloon that we need to pop. And 5 is popped. And 1 ends up becoming the very first balloon that we should be popping. Once we found our maximum value, we simply memoize it. This is the easy part. Once we memoize it into our two-dimensional array, it becomes fairly simple. So I just filled out this recursive function, and this is standard memoization, which all of you guys should be familiar with. The time complexity is O of n cubed. This is because for every element in this array, we create two subarrays. On the left side in green and the right side in pink. And every subarray takes O of n time to fill out the memoization table. So that is O of n squared. And since this happens for every element within this array, it's O of n times O of n squared. And that becomes O of n cubed time. And space complexity is O of n squared because our memoization 2D table is left and right, where left is always less than right. So you have O of n squared possible combinations in the worst case scenario. And that's really it, you guys. I will show you the code on Leetcode. This is our code. It's very similar to what I've already written. So this DP function that you see here is very, very similar to what I had just posted earlier on the slides. And we're essentially just calling this DP function in the parent function with the ones added to the bounds, and we have our memoization dictionary declared here. Notice I'm actually using a tuple instead of a two-dimensional array. You can do this either way. It should be fine. And if we submit this, we should see an accepted solution. And that's it, you guys. If you like this video, please leave a like and subscribe to my channel. It really helps the algorithm, and I really enjoy making these kinds of videos.